volt battery electric vehicle with ultra-fast charger demonstrator. A novel dual battery system concept was developed. A dual lithium-ion and lithium-sulfur battery system was designed, then the prototype was built and tested, showing significant energy improvement. An integrated measurement system based on electrochemical impedance spectroscopy was developed in order to estimate cell internal states through the hardware without introducing external noise. The system was successfully tested. Here is the complete list of the key achievements. It includes also the circular economy analysis with the theme of reuse or repurposing of the battery that was addressed, and the business model analysis, including safety, economy, social, and environmental impacts. As a final point, a potential panel of areas of improvement is reported. It includes the integration aspect, I mean integration with the vehicle architecture and the battery pack, of course, the battery management system partitioning and communication solution using wireless technology, the battery cloud management, the development of innovative materials and products with a focus on repairability and recyclability for eco-product design, the trigger of a resource relevant for end-of-life product, and the predictive maintenance with innovative technologies like digital twin, virtual sensor, or artificial intelligence. Now, please, let's move on the promotional video of the GHOST project.
Have you noticed? Electric and hybrid vehicles are everywhere. While this sounds great for the environment, the technology still needs drastic improvements, especially when it comes to lithium-ion batteries. At the moment, they are heavy, cost-intensive, and above all, not eco-friendly. The GHOST project is focused on creating the next-generation lithium-ion battery system, which is lightweight, recyclable, and cost-efficient with increased energy density. In GHOST, a new battery housing was designed consisting of long woven fibers molded with foam that saves weight and ensures durability even in extreme circumstances. When recycled, old housings can even be given new life. Built inside this housing is a modular lithium-ion battery system that can be easily assembled and safely repurposed and disassembled. So it's not only mass market ready, it's also better for our environment. Electrochemical impedance is used for sensorless temperature management and accurate state of health monitoring and tracking of the battery system. Stringent safety standards were top priority in the electrical, mechanical, and thermal design of the battery. To illustrate the modularity and scalability of the models, the GHOST battery system powers two very different vehicles, a plug-in hybrid electric passenger car and a full electric passenger bus with ultra-fast charge capability from a refrigerant cooling system. The work of the 12 GHOST project partners has optimized the electric, mechanical, and thermal architecture of onboard battery systems. And beyond that, they have contributed to future designs by developing methodological and technological know-how for modern battery systems. GHOST will have a profound impact on the complete chain from design and manufacturing to second life, repurposing, dismantling, and recycling of lithium-ion batteries. This means not only better performance, enhanced safety and reliability, and lower costs, but a viable and responsible solution for electric vehicles across Europe.
That completes my presentation. Thank you very much for your attention.
Okay, thank you. Just give me a second. So the next project which we'll be presenting will be Modali Squared. Modali Squared focuses on its first half, because it's still an ongoing project, on the development of models and characterization technique dedicated to generation 3B cells. This contributed to the implementation of a complete modeling toolchain from atomistic to cell level, which can then be used by end users such as material, cell manufacturers, as well as OEM. And the coming studies will focus on the behavior of solid-state batteries. To present this project, we have Martin Petit, who graduated from École des Mines of Nancy in 2007, obtained his PhD in chemical engineering in INPL in 2011. He joined IFPN battery modeling team as an electrochemical engineer in 2012 and has contributed to the development of electrical storage system models for system simulation in automotive applications, especially implemented in SimCenter Amesis Labs library. Since 2013, Martin is involved in activities around the lithium-ion battery safety modeling, and since 2012, he has been coordinator of the H2020 project, Modali Squared. Thank you, Martin. The floor is yours.
Thank you very much, Luca, for this introduction, and thank you very much for being here today to listen to my presentation. So, Modalis Square is a project dedicated to the modeling of advanced batteries, so next technology batteries, for integration into various systems. This project has been funded into the call of LCBAT6 in 2019. It began on 1st January 2020 and gathers partners from 5 countries. So we gather cell manufacturers with SAFT, material manufacturers with Solvay and Umicore, sales integrators from CRF, as well as software developers, Siemens, research center, and also SMEs. So this whole consortium has been built in order to gather a lot of skills difference needed for the new technologies of batteries that are seen today. The aim is to develop a new simulation toolchain that is fit for future batteries and that can provide information for specific battery users and stakeholders for the whole value chain of the batteries. So material manufacturers who are developing new materials need to have information on how the material will work into batteries. So that's the first part. Then the battery manufacturers need to optimize the cell design using these new materials in order to improve their battery design and get fit batteries for their customers. And finally, OEM and end users will need to be able to integrate these new battery cells with new specific behavior into their systems efficiently in order to avoid any issues in terms of aging or safety. And this is also covered by this project. So we decided in this project to target 2 main technologies for the future batteries, especially generation 3B batteries with high content of silicon. As you know, silicon has a problematic volumetric expansion that needs to be taken into account. And we focused our work on this in order to understand the behavior of silicon-based anodes and their impact on the whole battery, on the whole battery cell. And for generation 4 batteries, we need to focus on solid-state electrolytes, and especially the electronic conductivity in these solid-state electrolytes, how it behaves and what are the main differences compared to liquid batteries. And the main issue is that we have a lot of interfaces, and we wanted to focus on this interface to see their impact, how we can model it, and how we can take into account the change in the behavior of the interface along the lifetime of the battery. So the main achievement that we had in this project is dedicated for the moment to generation 3B batteries, where we have been working up until now. So first, we have developed specific materials and batteries, electrodes and batteries based on the materials that have been chosen. So we chose NMC 811 from Umicore as a positive material, and a blend electrode, a composite material with silicon oxide and graphite at the negative. So we had 20% of silicon included into this material, and this is important because with this amount of silicon, we can see the impact on the mechanical behavior of the composite through the lifetime of the battery. And it has a lot of impact also in the manufacturing phase and the issue with cycling that we can see from the first cycle of the battery. So the positive material was, as I said, given by Umicore. The negative material was a commercial one, so we need to characterize it. So we did specific characterization using SEM and TEM, and this allowed us to understand what was composing this material, especially with silicon inclusion into a silica matrix and embedded into a graphite layer. Thanks to that, it was possible to send them to the other teams in order to create a dedicated modeling of this material in order to understand its behavior or to predict its behavior. We did also the electrochemical characterization and specific swelling measurements using an electrochemical dilatometer in order to understand the swelling of the complete electrode when it's implemented into an electrode. So in parallel, we developed the atomistic and molecular modeling in order to understand the behavior of the material. Especially, some specific work was done by colleagues in University of Torino, CRF, and Gale technology in order to understand the behavior of the NMC material in terms of diffusivity, open circuit potential, and so on, and to also understand the mechanical behavior and properties of the silicon-based anode. So, as you can see, in this, we have been able to tackle the silicon oxide, the silicon, and the graphite to understand its properties and model them differently according to what was observed into atomistic and molecular modeling. So these parameters then need to be implemented into the continuum models that we are using in order to understand the complete behavior of the cell. Then the second focus was to understand the mechanical behavior of the cell. And this is also a multi-scale step because there are a lot of complexity in the materials that we are using into the negative electrode. So first, based on the TEM analysis that we did on the material, a specific work has been done to recreate this in FEM in order to understand the behavior of the composite material that is composing the particles of the electrode. This allowed us to understand how the particle was swelling in order to put it into a complete 3D FEM model to understand the swelling of the electrode and the electrochemical behavior resulting from this swelling. So it was done by Solvay in this case in order to understand how the electrode was swelling and some inhomogeneity that we can see in this swelling. And then also in order to focus on the aging and the degradation that we can see into the electrode composite with the binder and so on, DEM simulation has been done in order to understand how the grain and are working all together. And also, thanks to DEM, since FEM was not fit for such high deformation, we could also monitor the bonds between the particles in order to understand what was occurring during the swelling and how the bonds were deteriorating in order to evaluate aging of this system. Finally, this was implemented into a continuum model, so based on Newman approach, and simplified Newman approach, which is SPME, so single particle model with electrolyte. We are able to model the complete system with two particles, one for the graphite, one for the silicon, and take into account the mechanical behavior in terms of nominal working. So when the swelling of the particle occurs, we have a swelling on the whole electrode, so of the whole battery. So we can see how the battery is working and swelling within the system. And this is really interesting for interrogators in order to account for this swelling at the whole system level and take into account that the fact that the battery for one cell will grow from 0.5 millimeter. So if you have 100 cells, you have a higher swelling that needs to be taken into account in the system level. Then the mechanical behavior is also taken into account for the electrochemical behavior of the cell and also for the aging. So a lot of aging behavior are impacted by mechanical aspects. So we added into our model many aging phenomena, especially the mechanical effects such as particle cracking, loss of active material, and SEI cracking. So the aim of this is to create a complete tool chain. And so thanks to this first work on Generation 3B, we are able to communicate within partners because when you are talking to Atomistic modeler with modeling teams with integrators, there are a lot of different things that you want to, different languages that you need to use. And it's important to make sure that the inputs that we get from Atomistic are in line with what you expect from your continuum models. So that was the first step that has been done, and now we are able to get some parameters from the DFT into mechanical particle behavior, into DEM or FEM at the electrode level, and finally implement it into cell level. So this cell level is fit for aging behavior, so it's interesting for us to use that for 10 or 20 years simulated into our systems, and also for 3D cell behavior, when you can see especially the design of your cell and make sure that you have homogeneous behavior inside your cell. Now that this has been developed for generation 3, the work has begun also on generation 4 in order to understand the behavior of electrolytes. So the main subject of studies that we are using in this are sulfide electrolytes, especially ergodides, with several formulations. So this will aim at comparing the result from one formulation to the other, thanks to atomistic modeling, and then predict the new behavior when you change the formulation. And then we'll go to glassy sulfide, which is a new challenge, especially for atomistic calculations, which are much more complex. At the same time, we have adapted the SPME model for solid-state electrolytes. So the good point is that the electrolyte model that we are using is in line with what we expect for solid electrolytes. So it's the development is lighter. However, we need to develop a completely new interface for the negative electrode, especially that we have no particles, so single particles is not really well suited for this kind of approach. And this we need to create a new framework for this kind of approach in order to account for the specific surface behavior of the lithium, and then it changes over time due to dendrites formation or mostly surface formation. The atomistic and molecular will focus on mechanical properties and conductivities prediction on the electrolytes. And we have to develop also the experimental work in order to make sure that the experiments that we are doing will be comparable in the end with what we expected from the calculations. So the main impact that we want to procure with this, to give with this project is to fulfill future industry needs in order to integrate new materials and new battery cells into the complete systems. So this will give a competitive advantage to the European industries by creating links between all stakeholders. When Solvay is developing a material, it needs to be they need to show to their cell manufacturers that the material will be, in the end, more efficient or more suitable for their final use compared to a competitor material. And using the toolchain, they can use the results for their calculations in a complete cell simulation to say, okay, thanks to my material, your cell will last longer and you will have less resistivity or better interfaces and so on. The same way, a cell manufacturer can provide specific parameters for an OEM in order to efficiently integrate the cell into a complete car or system or storage system. Or they can improve or optimize the integration of the material into their own batteries in order to provide better batteries. And for OEMs, they can anticipate the new technologies in their integration of battery systems into their vehicles or electrified systems. So we are aiming at optimizing the cell development along the whole value chain from material manufacturers to OEM. And thanks to this modeling toolchain, there is also an improvement of the integration of the material of the cells in terms of design and geometrical properties. So the aim of this project was also to, as I said, to focus on new technologies, especially Gen 3B and Gen 4. So maybe for Gen 3B, we were a bit optimistic in the beginning in terms of achievements for silicon integration. However, it's still an objective to see some high silicon content by 2025. So this toolchain will be very useful at this time to use the models for these technologies in 3 years now. And for Gen 4, by 2030, this toolchain will be able to handle the behavior of the solid-state electrolytes for next developments. So I thank you for your attention.
Okay, thank you, Martin. I think we could see from the project also that the scope, due to the fact that this is a newer project, also has a deeper scope looking into cells and modeling, and this reflects the EU activities on the field of batteries. Next project, which is on the line, is De facto. De facto aims at developing modeling tools and digital twins of lithium-ion batteries manufacturing lines at cell level. And Elisabetta Ayerbe will present it, and she will briefly introduce the main targets of the overall project and describe the main achievements. Elisabetta obtained a degree in chemical engineering at University of Zaragoza in 2002, and a master in industrial mathematics at the Universidad Politécnica de Madrid in 2017. After several years working in research centers, in 2007, she started her current job as a project manager in Materials for Energy Unit at Citec. Currently, she leads the modeling and postmortem group of the unit, which works on the development of models for batteries. She has worked for more than 40 R&D projects, and she participated in more than 15 European projects. And currently, she is the coordinator of the European project De facto. Thank you, Elisabetta. The floor is yours.
Thank you, Luca, for the introduction. And thank you also, organizers, for giving us the opportunity to explain De facto progress, which I'm coordinating. So De facto, oh no, sorry. Should I? Okay. Yeah. Okay, I was saying that I'm coordinating De facto project, which stands for Battery Design and Manufacturing Optimization through Multiphysics Modeling. So this project was granted in exactly the same topic as Martin was mentioning. It was LCBAT 6 in 2019, and it was dealing with the modeling activities for cell design purpose. So De facto, we are 13 partners. CIDETEC is the coordinator, and we are in this road together with CEA, CERT, DLR, UPM Polytechnica, Fraunhofer, UNE, SCI, IRIZAR, ABE, Leclanché, TU Braunschweig, and Sustainable Innovation. So, yeah, basically, De facto deals with models, and it's approaching somehow to the digitalization of manufacturing. Models that are not only dealing with the cell performance, but also we are aiming to capture the certain manufacturing steps. So on the right side, you see the Gantt chart or the distribution of the work packages, and now I will later explain more in detail. So the project was starting in 2020, January the 1st, and will run out until middle of 2023. And the total funding was almost 6 million euros. So as I was saying, the overall picture of the overall aim of De facto is to gain more understanding on the manufacturing processes and how these processes are impacting directly on the cell performance. So we aim to couple manufacturing of the cell to aging of the cell in a way through different workflows, models at different scales, in a way that in the end we can suggest and provide guidelines on cell developments, but also attending on the manufacturing. In particular, what I'm talking is that in the end, we will know exactly which are the main parameters we should touch in the machines in order to have a certain outcome of or expected performance of the cell. So the specific objectives in the end, as we are relying on modeling, is that we need to carry out and we need to develop models that need to be really accurate so that they can mimic the real behavior of different steps in manufacturing, but also at a certain level of cell performance and aging. So we need accuracy in the models, but also efficiency, and it's it's quite difficult sometimes. But so this is the first and main objective of the project. But then we want to take advantage of these models, so in a way that in the end we will build a closed loop between these models, manufacturing and characterization, in a way that we will provide guidelines on how to improve these cells in order to achieve certain targets, and the targets were already set in the topic. So by this approach, we are aiming also to reduce the experimental load by a factor of 3. Also, we are completely aware that we are not only focusing on the technical aspects. Obviously, we need to improve cell design, we need to improve cell performance, cell aging, but we wanted to also provide some guidelines on the standardization, because we are completely aware that at certain level there's a certain gap in this area. And from our perspective and from our knowledge, we could somehow contribute in this area as well. And obviously, as we aim to reduce the experimental load, and also therefore we expect to reduce the cost, we expect also to reduce the time to market achievement. So these are the main objectives, and here this is the figure that explains more or less the overall picture of the project. So we have like 3 blocks in general, although the main one is the modeling. So we have the modeling, sensitivity, analysis, and optimization box. And then also in green, you have the prototyping and industrial manufacturing, while we have the third blocks is dealing with the characterization. Let me start with the prototyping blocks in which we manufactured not only prototyping cells, but also industrial cells, large cells. And what we want is that we have already built these cells, and we have started characterizing. I don't know if you can see, yes, you can see the mouse. Okay, so we have worked on the development on these manufacturing cells, and we have started characterizing them at the different scale levels, from material to electrode up to the cell level. And then this is a very critical and important step in order, in order to build these accurate models. We need to get parameters, we need to accurately describe the mechanisms. So it's really important to have a big connection and good connection between characterization and modeling effort. So once we have this connection, we are developing models in which we need to capture all the physics in behind, but then we need these parameters. By having these models, and once that these models are validated, we will return to the prototyping box in the way that we will provide these guidelines to improve and optimize chemistry. So within the factor, we will stick to the generation 3B technology. So we will have NMC 622 graphite industrial scale cells. It will be large cells, between 40 and 60 ampere hours. Also, we will be dealing with NMC 811 graphite silicon, and these cells are prototype level, in which the electrodes are manufactured at a pilot line, and also they're sold in a pilot line facility. And also, we will jump at certain level to the LMNO, graphite silicon, but with the main idea of providing guidelines how to improve the models in order to capture the mechanisms in this chemistry that are not covered within the previous chemistries. So this is the main picture of the project that explains the general activities. And as I said, the main objective of the project is to gain more understanding between manufacturing and cell aging, and coupling both aspects through modeling. Okay, so far what we have achieved is that regarding manufacturing and experimental load, is that we have manufactured industrial scale cells. Also, we have developed prototype cells, NMC 811 graphite silicon, and we have started characterizing at all the scales, from material to electrode, also cells. And also this is very in line with the modeling activities, because at the modeling we are facing, or we are approaching in these different scales. So we have particular needs from the modeling developments that need to be filled through this experimental work. So basically, obviously, we are characterizing material at a structure level, composition, and so on. We are getting parameters for feeding all the scales models, like for instance in here the tortuosity, but many, like around 40 parameters at the continuum scales, and similar to the mesoscale as well, that later I will explain. And also we are having certain experiments, particular experiments, to capture certain steps in the manufacturing, such as the electrolyte filling steps. So we already assembled one specific setup for that. And then once we have built these cells, we are performing electrochemical aging in order to understand different degradation mechanisms, and now we will start carrying out post-mortem analysis in order to figure out the main mechanisms that will be later implemented into the models. So these are the advances on the experimental load and cell manufacturing. And now coming to the modeling, as I was saying, that we have like two blocks or two main activities in the modeling. Is that the first one is on the manufacturing, and the second one is once the cell is already built or developed, and we run a aging test or cycling test. So it summarizes all the achievements into the manufacturing. So talking about the manufacturing, I already said that we are focusing on the lithium-ion cell, and we are mostly focusing in the current roll-to-roll electrode processing step. So basically, in the modeling of manufacturing, we are focusing in two main steps, two main critical steps, which are the electrode processing, and the other one is the electrolyte filling. So coming to the electrode processes, there are like three main steps that are really time-consuming and are critical, because they fix the structure of the electrode that later will last more or less depending on the particularities. So I'm talking now about the slurry preparation of dispersing, drying step, and calendaring. So first, what we have done here is to set up all the models regarding this electrode processing. So you can see, I hope the video is working. Now, within the models regarding dispersing, we are capable to predict rheological properties of the slurry. So it's really important property if you want to have a very good performance on the coating step, and then obviously good performance on the electrode. So we are capable to predict these rheological properties depending on the CV agglomerations. So, and now they will be working on the sensitivity analysis to identify which are the main or critical parameters in this particular step. Then jumping to the drying step, that indeed it's a very time-consuming and also energetically talking, very cost-consuming step. So here we are developing, we are currently, or they have already developed CFD-DEM approach at 2 scales in order to, again, identify the main critical parameters in these steps. In the drying step, you have different mechanisms. You have sedimentation of the active material, you have evaporation of the solvent, and also migration of the binders. So it's a very critical step in which at the end you get a final structure or microstructure of the electrode, and depending on this might last longer or less. So they are already, the models are already set up. I'm running the video now of the drying step in the unresolved approach, and also in the, Oh, yeah. I don't know if it's going to work. I don't know why, but it jumps. I'm not able to move. I don't know how to make.
Just try maybe this one.
Okay.
No?
No. Yeah, apparently it's just above this plot.
If you click just in the middle.
Okay, okay, you manage. Okay, maybe.
Smart. Come on. Yeah.
Okay,
Sorry.
maybe you can put play.
If I manage. No.
No, okay, it doesn't matter. Don't worry.
Okay. Sorry.
But okay, you can imagine. Otherwise, you can ask me for a picture afterwards, or you can directly contact myself. Okay. So within these steps, they are resolving DM coupled to the CFD, and then they can correctly capture the thickness evolution and porosity of the electrode, which is very important parameter in the next steps. So this is what they have done so far. And we have done so far, and now again, they will carry out sensitivity analysis in order to identify the main critical parameters. And here it's really important because this step is particularly energetic consuming. So then jumping to the calendaring is like the final step in the electrode processing. So electrode is inserted into between the two rolls, and then you put pressure in it, and then you finalize or freeze the microstructure of the electrode. And this stage, we have developed discrete element methods for mimic the calendaring behavior. So now we can predict certain thickness, porosity, and even tortuosity values for certain parameters of the machines, which is really important. And this is all about the electrode processing, and jumping to the filling step. Again, filling step, it's a time consuming, and it's really important to know exactly how the wettability of the electrolyte behaves in terms of this process. So they have already set up the lattice-Boltzmann approach for identify or correlate the impact on the electrolyte penetration into the pore, and it's already available paper in it. So now jumping to the modeling, but on the cell performance, we are very much focusing on the cell degradation. So, but particularly we are emphasizing the mechanical degradation. So again, we are covering the different scales, starting from atomistic approach, and then mesoscale and continuous scale. So far we have set up all of the models, and you can see some images here. So in here we are able to capture how the lithium silicon is behaving because of the swelling of the silicon. Then obviously mechanical aspects are also captured in these two approaches that are complementary at the mesoscale level. You can see now the video in here. And also we have developed this continuous scale model in the whole dimension of the cell. And this is the continuous scale model has been then reduced by advanced reduced other models. And this is an open source, and it's available to the community. So I will later explain. And this is the tool that will be also used for optimization purpose to guide manufacturers in which component we should modify to achieve certain parameters. So now, I don't know. Oh, I don't know. Okay, so this is about the open source that we have just released, and is available in our website. So it's a P4D coupled to the reduced order models, and it combines the CDMO tool, which is available in GitHub, to ECROM, which is the reduced order models. Obviously, once if you are interested, you can download all this information, and you have the programming manuals, installation guide, and also the tutorial available. and it's released under this GPL Afero license. Okay, this is from the technical part, and yeah, we also been contributing to the standardization. So we have in mind to launch 2 proposals for Sense and Elec workshop agreements. We have already submitted the first one, and it's on the data required for modeling of the material, cell, and manufacturing processes, basically because we are aware of the importance of the data acquisition and protocols and so on. And the next CWA will be on the experimental and characterization techniques to achieve this data. Okay, also we had a workshop on the digital approach, in which we had opportunity with different cluster 5 projects to discuss on modeling approaches. We've been presenting the factor in different events, such as the clustering event and also battery innovation days. And then regarding the mid to long term, this is a picture of we should talk about in different aspects. So from the technological point of view, we have set up the models, but still, if you think how we should approach to the digitalization to gain flexibility and to gain more understanding and also gain sustainability in the production line, also we should move towards digital twins, and still we are a little bit far from that part of aspects, because the models we are developing are perfect for gain understanding, but still need to be worked for in computational cost. So we need to carry out certain activity is improving the cost efficiency of these tools, and maybe artificial intelligence might play a critical role here. Also, from the environmental point of view, obviously we are contributing because we are dealing with the drying. We are modeling the drying step, which is a critical step in the manufacturing. Where you have a NMP solvent evaporation, and you have to deal with that. Also, it's very energetic consuming, and so we have some work on there. And also, we are expecting to enhance durability. So therefore, you improve environmental in that sense. But it's true that we are not dealing with the skills, or we are not training, or we are not generating training documents for training or educating workers in this area. So it's something that should be included in the longer term. Also, from the economical perspective, we are already contributing from the factor, because we aim to reduce the time to the market and reduce the cost of manufacturing. So this is something we are already doing in the project. And then it's true that for the societal impact, we need to still think more on which are the societal impacts, and think in a way that we should insert these impacts into our own tools to improve them. And then also standardization, it's a critical, or it's a very important aspect in which we are somehow contributing, but there is a long way to still work on. So because data needs to be standardized, communication, many aspects, models, validations, there are many aspects that are still further a little bit work on. So yes, with this I would like to end. Thank you very much. If you have any comment, you can reach me in this email, otherwise later on. Thank you.
Great, thank you, Elisabeth. I think we have, with the fact that we conclude the overview on modeling and characterization of cells, but thank you for your presentation, especially the part where you speak about the dissemination and having made the open source tool available, and your final reflections, which I think will give fuel to the Q&A. Okay, the next project is IMAGE. IMAGE is a concluded project. I think has a slight different purpose than the previous 3 projects, because IMAGE focuses on innovative manufacturing routes for a next generation battery in Europe. The presenter will be Wolfram Koz from AVL. Wolfram finished his PhD in technical chemistry at Graz University in 2005 with focus on lithium-ion anode materials. Then he worked for Roche Diagnostic in Graz in the development of electrochemical sensors measuring glucose, oxygen, carbon dioxide, and ions in blood. Afterwards, joining Austrian Institute of Technology in Vienna, he worked on 5-voltage lithium cathode materials and was technically responsible for the installation of a lab-scale production for a laboratory for lithium-ion cells. And since 2017, he's working at AVL, supporting automotive battery development project, and has been the project coordinator of IMAGE. Thank you, Wolfram.
Thank you. Thank you very much for the introduction. I'm glad to be here today and to present the results from our IMAGE project. Oh, that does not work. Wait. Double click. Oh, I don't like it. Enable. Yes, works. Okay. IMAGE is also a research and innovation project from the 2017 Green Vehicle Calls. Some project core data, the budget was close to 5 million, and this is 600 working months, equaling 50 years of work in total. The project started in late autumn 2017. It was originally scheduled for 42 months. With an extension to the corona pandemic, we made it in 48 months, and official end was October last year. The consortium consists of 13 partners. Let me introduce them very briefly. We have RWTH Aachen, Freie Universität Brussels, and Graz University of Technology for the scientific part. We had CITEDEC and CIC from Spain, both Basque Country, for the research institutes. And we have for the many partners from different parts of the industry, beginning with Umicore. They are known for recycling, for noble element refining, and in our case, most important for NMC manufacturing. We have Hydro-Quebec from Canada as a partner. They are in lithium production and research on lithium. We have Manz from Italy, which is a mechanical engineering company providing equipment for cell manufacturing and capacitor manufacturing industry. We have also from the material manufacturers Arkema in France. They are providing electrolytes and membranes for separators. And we have finally Varta and BMW as OEMs, and ABL is an engineering provider. So IMAGE was one of the first projects with the clear ambition to bring back competitiveness for the European cell manufacturing battery industry to Europe. It was in 2017, the idea was to take some novel battery materials, not state of the art at that time, to put these materials together to build a new generation of cells, and by this circumnavigate the dominance of the Asian cell manufacturers. And from this ambition derived, the objectives are clearly production techniques, more efficient manufacturing technologies, and overall bring together the academic and the industry world and put up some production framework. The IMAGE cell was conceptualized to be of a lithium anode, to have an NMC 622 cathode. The novelty is it is aqueously processed, and to combine this all with a Gale polymer electrolyte separator. So overall, the system should be more efficient in terms of energy and more environmental benign, and also offer the advantage of a higher energy density. So to go into the field of material development, the highlights, we used lithium metal foils of 40 micrometers. Smaller sheets or thinner sheets are possible. 20 microns are possible, 30 microns are possible. If you want to go for an anode which is not supported mechanically by a current collector, you rather go for 40 microns. The cathode, the NMC was from Umicore, as mentioned. First attempts were with normal NMC. So if you take a normal NMC and do it in a water-based process, it does not work out. The active coating is rather brittle, and the adhesion to the aluminum current collector is very bad. So some modifications had to be done there, and also the manufacturing of the cathode tapes had to be optimized afterwards. And the third major component is the Gale polymer electrolyte. Here, Arkema did a big job. So you have a material which you combine with an electrolyte, which starts to swell, and you have to make an optimization for mechanical stability, for the swelling properties, and afterwards for the conductivity of the system. So this is at least 3-factor system, and if you only optimize one of them, it will the other 2 properties will go down. So this was quite a challenge. The next step was bring together these materials and to start building up cells. For cell assembly, there are basically 2 ways to find out. We found out. So it's either you take the components, which is cathode and separator, and bring it together with some electrolyte, let it soak from the outside. So under very controlled conditions, the soaking is very good, but the handling afterwards is rather very problematic. Or you go for the other method, you do an assembly of the dry components first and put in the electrolyte afterwards. So the second method is more familiar, or is more closer to what we have in the state-of-the-art cell manufacturing today already. It also turned out that we get with this method the more reliable cells, the more reliable results. However, the process is still far more complicated than with state-of-the-art cells. So lots of coin cells were made in the course of the project, mainly to study the materials, material properties, make a characterization of these components. Then monolayer pouch cells were built, and finally also some multi-layer pouch cells of close to 2 ampere hours were built and characterized. The small cells were rather characterized or tested at the material manufacturers and at the universities. The multi-layer cells finally were rather tested at Varta, at BMW, and at AVL. I put in one of the pictures showing one of the cells from Sidedek in a fixture which is measuring the volume changes. So as a takeaway, if you upscale one of our 2 ampere hour cells, rescale it to a modern 60 ampere hour cell, and volumetric energy density of 850 watt-hour per liter is possible, also 450 watt-hours per kilogram. However, the cells we could build in our project, the cycle number is not it's not good enough for automotive industry at the moment. So the next activity in the project, if you go for new cells, cells of a new noble chemistry, was how to build up modules and battery packs afterwards. So we double-checked what's the theoretical swelling of these systems, of the cell systems, what's the expected pretension force needed. So this is, in our case, the major properties which are changing. And we found out with the results from the first monolayer cells that it is possible to go with a rather conventional module concept. So we were discussing already pneumatic systems or hydraulic systems for the pretension, for applying a pretension force, a defined one. It showed up, or we found out that with some conventional compression beds, not conventional, but with compression beds which are under development at the moment, it's also possible to buffer away the volume changes and to apply the higher pretension force needed for the Gale polymer electrolyte cells. So this was based on the cell testing. And I'd also like to highlight another activity of our project, which was done by CSE. So it was going beyond Gale polymer electrolyte. So it was a screening of what is in literature on solid state materials in general, of all types of chemistries of solid state materials. It is a focus on material properties. So how do they fit into battery industry in terms of the properties afterwards needed for separator and for compatibility with anode, cathode. And also it was a review for the different ways of synthesis of this material described in terms to double check the manufacturing. Please, if you see these results for material requirements or action requirements, keep in mind this is reflecting the state of the art. So with every innovation coming up, this will change a bit. And also, to my understanding, not every all solid state material is compatible with every way of manufacturing described herein. So this is another major topic of our project. Let's come to the impact of our project. So there were some specific questions in the draft of this presentation. So I'd like to distinguish the impact in a technical impact and the social impact. The technical one is we learned from our cells, if you go with lithium metal, you can increase the energy density, of course. The manufacturing is easier, it's less complex. You avoid preparation of anode tapes, so it's less energy intensive also. A cathode which is manufactured by an aqueous way is environmental more benign. So that's the key technical impacts. And from the other point of view, from the social point of view, there was the opportunity for a new generation of students to learn electrochemistry in an industry research project. So I had the opportunity some years ago myself. So it's seeing what industries is working like, what scientific institutes work like. So it was sometimes a bit of a challenge for me. There are frequently new faces, but overall I think this is a very positive point to mention from the project. Also, a collaboration between the partners was enabled, respectively intensified. So some partners knew each other before, but many of them were very new to each other. I'd like to mention we have 24 publications at the moment. To my understanding, some more will follow, as not all results we have achieved have been published so far, and one patent has been filed. Coming to the question for the impact, what in terms of future research is needed, I would answer material research, development of material. So I would guess about 90% of all improvements come from materials. So if you think, for example, multicrystalline and monocrystalline cathode materials, it's material research. If you want to go for LNMO, you need an electrolyte which is compatible with very high potentials. Again, it's material research. Market uptake, I think it's the aqueous prepared electrodes, the Gale polymer electrolyte. the lithium anode and the solid-state battery technology at all in this order. The aqueous prepared anodes are state-of-the-art already. Aqueous prepared cathodes, I'm not sure about the market penetration, to be honest, of this technology. It's feasible for NMC 6 to do. To my understanding, it's not feasible anymore if you go to higher nickel content NMC. I see a high potential, market potential for the Gale polymer electrolyte as a new type of separator material. Lithium anode and all solid state materials will come later, to my understanding. They will need some more years. Impacts, results were in line with the Green Deal goals from the European Commission. I'd like to mention the reduction of organic solvents usage, less energy required production processes, and overall a battery based on a lithium anode, on a lithium metal anode, principally comes with a higher energy density, so increased driving range. Respectively, you can make the battery smaller for a given or expected driving range. Follow-up plans. I observed the partners collaborate again in new Horizon 2020 projects. Also, I'm aware of some industry projects between the partners. I'm rather sure there are more because industry doesn't like to talk about their projects so much. Benefit for other projects is an interesting point. So we did not have so many meeting points with other European Union projects in this project. I would say there's a major indirect benefit. So we also benefited from the learnings from previous projects, which ABL did, respectively, which I did at AET. And I think what the partners learned in this project will be further be of big usage for all future projects the partner will participate in. And also a major benefit I see in the manufacturing roadmap from CRC, where they summarize their findings on the solid-state materials. With this, I'd like to close, and I'd like to say a big thank you to the European Commission for this project in general, for the invitation to come here, for the organization of this conference. It's a lot of work, I understand. I did it once myself. And I'd like also to say thank you to all partners, to all project partners. Also, they are not here at the moment, so Corona pandemic was quite a challenge. So having some tests running in your laboratories or having some synthesis running and then your facilities are closed down, it is a nightmare. And everyone kept working, and everyone was trying to minimize the implications of these lockdowns on the project.
So let's directly jump into the question and answer session. So my name is Marlena Fork from AVL. Thank you very much that you are still attending us and giving us your attention. Also a big thank you to the speakers who really did excellent talks and very interesting new insights into modeling, manufacturing, as well as battery design. I'm sure you will have some questions to the speakers. Please be so kind to give your name and your association.
Hello, my name is Jordi. I'm from IREC. It is not really a question, maybe it's a thought, or let's see if they can actually say their opinion about high loading electrodes, especially affecting the cathodes. How they consider that factor into their simulations, and how do they see, achieving high loading in order to achieve high energy density cells, the role of the conductive additives? Do you think that that can be, we can skip that at some point? But just you know, to know your opinion on all these topics.
Okay. Can you hear me? Yeah. Yeah. So the high loading of electrodes, I know that or cathodes can be accounted for by the modeling. So the main aim is to correctly characterize the electrode first, and usually, as we are doing physical-based modeling, we should have some information on the impact of the calendaring and or at least the impact of the loading of the electrodes that should be taken into account, and especially for the negative electrode, for instance, if we have a high loading, there will have also a big impact on the mechanical behavior if we have silicon-based anodes, and also on the lithium plating. If we have high thickness electrode, we should have also some issues with the global potential on the electrode that needs to be taken into account by the models. So that's the point also of the modeling, is to predict such behavior, to say, okay, we have a new ID, we want to assess the benefits of a high loading electrode. Does it have a real benefit in the beginning? Does it behave still good after aging and so on? So that's an important point to be taken into account, of course. And also for all solid-state batteries, we saw yesterday, for instance, many techniques with separated electrolytes. I asked these questions, and I think also modeling can be of help here to know whether it's a good point to have two electrolytes for the positive and the negative, or where to put the interface between the two electrolytes at the negative interface, at the positive interface. It can be taken into account for that, and it's a good point for the modeling part also, in the prototyping phase at least.
Yes, similar to what Martin was saying, within the factor, there was one specific target in the topic, and through these models, we should achieve like around 300 watt-hour/kilogram. So as we stick to the lithium-ion, we are forced to go to high loading. So this is currently covered within the models that we are currently developing, although we will start, we have a start with manufacturing like reference electrode, typical electrode thickness, not really high loading, but obviously we should also take into account the difficulties in the high loading, even transport limitation and electrolyte depletion if you have high C rate with a high loading, and also interface issues with in the cathode, but not only in the cathode, but also in the anode. So it's something that we are dealing with, and through models we are sure we can capture these mechanisms, and somehow we can also correlate to the manufacturing parameters. So also it's important to identify the main parameters in the manufacturing to stick to that high loading electrodes.
Please, any additional question? Yeah.
Okay, thank you. Thank you for the description of the project. My name is Joshua. I'm from Citetech. My question is for you, for Martin. The simple questions. The shape of the cells you have modeled are pouch, cylindrical, or prismatic? This is the very first question. The second would be, I noted here, for example, that the percentage of silicon that was in the anode, it was 20%. With these models you are developing, can you foresee beyond this percentage the behavior of the anode? Thank you.
Yeah, so we chose pouch cells, especially to focus on the mechanical behavior. So if we are using hard casing cells, we would prevent some mechanical behavior that would was less visible. So that's why we choose this kind of cells for the project. And also for the loading. So in the model we have a parameters for the loading of silicon. We can change it to see the behavior. So for instance, what we can see for the moment is that we have two phases in the charging of the battery. The first phase where the silicon is charging, and the second phase where the graphite is loading. And we can see a change in the swelling rate of the battery due to this due to this repartition. And if we are changing the charging rate, this swelling will change also. And if we change the amount of silicon, there will be a change in this kind of behavior. And what we want to do is to have the most generic approach possible in order to account for variability in the the processing, variability in the materials, and variability in the mixing and formulation of electrodes. So if we want to do that, so for instance for DEM, we will have some kind of springs that will model the mechanical behavior of the cell, and we want to evaluate the stiffness, and this will not be impacted by the amount of silicon or graphite, and we can adjust this to see the implication of this amount of silicon. So for the moment, we focused on the formation that we have in real life to compare it with the model, and then we will extrapolate to see the implication of higher silicon content and so on.
Any additional questions from the audience?
Hello, Ian Faya from Bosch. I'll take the mask. Hard to talk with a mask in front of your face. First of all, it's very nice to see that a previous project that was finished in 2018 led to this topic, that led to these wonderful projects that have been completed now or on the way to completion. The question I have is, how do you validate, I might have missed it in the presentations, how are you validating the simulation results, especially for phenomena that are taking place at the microscopic level, where there might not be measurement technologies available for these kind of validations?
Yes, within the factor, as I already said, we are covering the characterization at different scales as well. So we have a capability to characterize not only the material and the cell, but also electrode. So for instance, there are some partners with the capability to perform tomography measurements, so they can, and then also they can monitor online the evolution of the thickness swelling along the charging and discharging. So having this information and comparing to the simulation results, for instance, in the microstructure with the DEM approach, is the way we validate the codes, in particular to this specific phenomena. But it's similar to the different scales. So it's similar to the cell level scale, in which we can monitor the thickness evolution, for instance, and then we have simulations, and we compare simulation against experimental. So
it's the same for Modalis. So we have specific techniques at all length scale, from SEM and TM, to see the variation of material composition, especially the silicon. We know that from silicon oxide we can have some reaction path with change of the silicon oxide to silicon with lithium oxide and so on. So we are monitoring them. We have dismantled coin cells that we have cycled in order to see the evolution of the silicon and the layers, interface layers, to see also if there is some more. We've seen that some SEI formation, high SEI formation from some cycles that we can monitor. We have for the, as I said, for the electrode level, some specific dilatometry tests to see the swelling of some electrodes without counter pressure. And finally, at the cell level, we have developed a dilatometer for the cells in order to evaluate the swelling, as was presented by from AVL for this project, for image project, in order to see the impact of the pressure and the impact of the swelling, and correlate this with the model. But in the end, some parameters are not directly measurable, so it's complicated. So we have to make some guesses from what we observe. especially from specific checkups and so on to analyze the aging, to see whether what we make as assumptions are correct or not, whether the aging that we see are compatible with, for instance, loss of active material, loss of lithium inventory, and so on, and relate them to the models.
Maybe just one comment. The swelling, you can calculate it theoretically, and at least in our project, the numbers we afterwards measured, they are in the same range, but they are lower. So some of the swelling is compensated within the cell already. So I would assume it's the separator which compensates it. So in our case, the Gale polymer electrolyte, but you don't see, at least with modest C rates, you don't see the swelling which is theoretically possible on the outside.
Any other question, maybe? No question, so maybe one question from my side. So we had a lot about the modeling tools. Is there some kind of natural limit or some kind of complexity limit in terms of interconnection of the different aspects or running time of some modeling and so on? Is there any limit you see, or can the complexity be increased to us, or what is the extent of complexity? Or what makes sense in terms of complexity here?
I think it's a really interesting question, but difficult to answer. But complexity, obviously, models have huge complexity. So, for instance, in the continuous scale, you have partial differential equations that obviously. So first, you need to identify the best equations that mimic the reality, and this is time-consuming, and very. You need to do it in a link way with the characterization, because in the end, you need to have a real behavior within your models. And once you have identified the equations, you have to solve them numerically efficiently.
Yes.
And it's a new challenge there because it's mathematics, and so you are combined. It's like a multidisciplinary approach. You have chemistry, physics, mathematics, and then computers as well. So
I think the connection of these different professions is also a rather challenge, right?
Yeah, and it's the connection is difficult. The language sometimes is also difficult, but we are moving forward. So I'm certainly optimistic.
You're learning from each other, right?
Yeah, sure.
Yeah, there are a lot of changes over the years. For now, there are still things that cannot be done directly or difficult for instance, for ab initio modeling. Once we don't have crystals, for instance, it's more complicated to cover. The colleagues from Italy working on the ab initio modeling for Modalis saying that once we are going to glassy sulfide, there will be a very big complexity that cannot be come up within the scope of the project. We need to find some solutions for that. Also, we discovered that some simulation techniques were not fit for the new materials that we are using. FEM modeling for silicon-based anodes were not very fit because of the high deformation that we had. So the deformation were too high and not represented correctly by this system. So we needed to switch to other description like DEM and so on, with other limitations. So we are a lot of things to learn still for that, but with the amount of the computational power that we have now, it's easier and easier. We need also to focus on the right time scale and right length scale for what we want to do. For instance, if we want to go for aging, for 20 years aging simulations, it's very complicated to go with the fully resolved 3D modeling, but doing some 1D modeling with specific assumptions, it's fast enough, and we have sufficiently good results for that. So with a good choice of assumptions, it gives us sufficiently good results to predict the behavior of the cells.
Maybe one last question?
Because otherwise, the next RTR conference is only 1 year, so you have to wait 1 year. Make one question.
So I think if not,
Yes, then.
thank you very much.
No question, but just to conclude, well, big thank you for all the participants once again, also in the room here. The next appointment is actually the closure meeting, the closure, let's say, summary meeting, which will be held in the big meeting room downstairs. It will start in 10 minutes, so there is no coffee break in the meantime. So I hope to see you, everybody, in the big meeting room soon. And otherwise, we see, hopefully, face-to-face at the next RTR conference in 1 year, pretty much. Thank you. Have a good rest of the afternoon.